Well, maybe we can start. So, good morning, everyone, and thank you for joining us for episode 9 of the EcoGen webinar series. Before we begin, I would like to go through a few housekeeping notes. So, please mute your microphone when you're not speaking. Use the chat to drop your question, and we will address them during the session of discussion later on. Raise your hand when you want to speak, and just so you all know, recording is in progress. So if you don't want to be recorded, please keep your camera off. So this is the agenda of today. Our 3 speakers will explore how livestock breeding and management practices can support climate adaptation and resilience. Each presentation will last approximately 20 minutes, followed by the 20-minute discussion session. And again, please feel free to submit your question in the chat throughout the presentations. Without further delay, it's my pleasure to introduce our first speaker. Mario Calus is a full professor and chairholder of the Animal Breeding and Genomics Chair Group of Wageningen University and Research. And his main area of expertise is on genomic prediction and genomic selection of a variety of livestock species. His presentation will focus on the impact of heat stress on fertility traits in dairy cows in the Netherlands. So please, Mario, when you're ready, if you want to share your presentation, I will stop sharing mine.
Okay, thank you for the introduction. So today I would like to share some results of our research that we did on the impact of heat stress on fertility traits in dairy cows in the Netherlands. And this is work that, amongst others, I did together with my colleague Jeremy van der Plas. And I'd like to start with acknowledging the RUMIGEN project that funded this work, and CRV, a cattle breeding company based in the Netherlands, that provided us with the data to do this work. So if we think about heat stress, and then particularly on the potentially negative effects it may have on fertility, is that just at a very basic level, there's a couple of things that may change or go wrong. So one thing that may happen is that estrus detection is more difficult because the cows simply show fewer signs of it. And then if estrus is detected and the cow is inseminated, fertilization success may be lower. So this is often assigned to observations that the quality of oocytes under hotter conditions may be poorer, for instance. So we were particularly interested in heat stress, or the impact of heat stress on fertility at different levels. So first of all, at let's say the average population or the phenotypic level. So there we looked at, we kind of monitored based on historical data, average levels of fertility and how that tends to decrease with increasing THI. So THI stands for the temperature humidity index, and I'll show on the next slide a little bit more on how to interpret these values. And particularly the question that we have, at which THI level, which kind of translate to a certain level of average daily temperature, do we notice that heat stress starts, so that fertility starts to decrease because of the hotter conditions. So that's on average on the population. And then then we are, as geneticists and breeders, we are particularly interested if that performance on average goes down, what does that do with the individual or the genetic differences between individuals? So if we talk about this, we would normally talk about genotype by environment interaction, and we can expect two things that may happen. There's a change in scale, so differences between individuals become smaller or larger, but it may also lead to different ranking, which basically means that under some conditions, the best animals under some conditions are not necessarily also the best animals under other conditions. So the question here was, how large are those changes? And we try to address that. So to clarify the relationship between temperature, humidity index, and temperature, well, it's the name already indicates it has humidity in it. So basically, this THI is a function of temperature, and it also considers the relative humidity. So I plotted here for 4 different levels of relative humidity, which are sort of the typical range of relative humidity in the Netherlands, that given a certain temperature, what the effect is on the THI. And you can see that certainly if it's a bit cooler, the relative humidity doesn't really affect the THI, but particularly on days where it's hot, then the relative humidity becomes more important, and a higher relative humidity means a higher temperature humidity index. But just looking at this, I think it's fair to say that the THI is driven mostly by temperature and much less by relative humidity, and then only at the higher temperatures. So if we then start to think about the impact on fertility at the phenotypic level, so what we do in this kind of studies is that we kind of model or monitor fertility as function of THI on the x-axis. If we would just do this at the phenotypic level, what we may see is that, and this is just sort of a schematic overview of what's possible, is that individuals up to a certain point in THI, they have a stable performance in terms of their phenotype, but then after it, the performance of all the individuals goes down. And then across all the individuals, the first thing to measure is what is the population mean, and how does that population mean change as function of THI. And then based on this curve, we can observe a THI threshold that determines the onset of heat stress, so where the performance really starts to be affected for all the individuals in the population. And then if we talk about the genetic level, then we are more interested in the deviations of individuals, indicated here by this green arrow, from the population mean. So this individual performs above average, both below and also above the threshold. If we then further into the genetic level, what we actually do, if we go back to the previous slide, we take this curve for each individual and we subtract the population mean from it. And then actually here, if we model this correctly, we no longer would have the phenotype for fertility, but preferably the breeding value. So if we do that, and I'll show later in my results that we've actually done this, what you get is that we estimate a breeding value for what we call intercept. So the intercept is basically, it's the horizontal line of the individuals that indicate the phenotype or breeding value until the THI threshold, not affected by heat. And then we also want to establish a breeding value for slope, which indicates relative to the population mean, does the individual perform better than average as this one, or does it perform poorer like this one that has a negative slope. And then in our models, we want to estimate the genetic correlation between this intercept and slope to determine, okay, if we just select on higher breeding values for fertility when there's no heat stress, so below this threshold, do you automatically also get individuals that are not as affected as much by heat stress after the threshold? And this model that we use here is called a broken stick model, and that's the name comes from just from the curves as they look. It's like kind of a stick, and it's
So you
broken
said that you want
at
to
the
take
moment
you
of the
to
threshold.
that.
So the data that we used is basically all Holstein data in the Netherlands. We looked at first lactation animals for different traits. So conception rate at first insemination, interval calving to first insemination, interval first to last insemination, and calving interval. And you see that for most of the traits, we had more than 400,000 records, but a bit fewer, 100,000 fewer for calving interval. And then after having done that, we also looked at additional other parities, but only for conception rate. So here we have parity 1, 2, and 3. So these are all lactating animals, and parity 0 means basically maiden heifers. And you can see that this number here is exactly the same as this because it's as this one because it's the same data, and the others there are a bit different. So the THI was obtained based on information from the nearest weather station, which was about 15 kilometers on average away from the farm. And we then averaged these values across 3, 7, 10, 30, or 50 days surrounding the insemination to see what was the best definition. So to jump right into results, so basically what we saw is that it was better to define THI in a short interval surrounding the insemination. So the results that we have here are just sort of moving average for 3, 7, and 10 days around insemination, and they coincide very nicely with each other. So what you see here is there's some erratic patterns at the beginning, at the end, due to relatively few observations. But overall, there's a couple of nice trends that arise. So for interval first to last insemination, we more or less found that the THI threshold for the onset of heat stress, so the decrease in fertility, because here a higher value means poorer fertility, was at a value of 60. For calving interval, it wasn't all that clear. It seems to be lower and even closer to 50, but also the pattern here was a bit different from what we expected. Then if we look at conception rate, here we also very clearly see a threshold of THI 60 across the different definitions of the THI. And for interval calving to first insemination, there seemed to sort of an overall decrease with higher THI without a clear threshold appearing in the figure. So then staying with conception rate, but then looking at all lactations. So here we have the 3 different lactations. So 0 means maiden heifers, and 1, 2, and 3 is parity 1, 2, and 3. So what you can see is that for parity 1, 2, and 3, they sort of nicely align, and they all obey the same threshold of 60. But for the maiden heifers, we didn't really saw a trend. It's at best it's decreasing a little bit, but this was not really statistically significant. So even at a THI of 70, there was not much evidence for heat stress for conception rate and maiden heifers. So as said, we were also interested in the genetic level. So there what we did is we modeled the genetic variance as function of THI. So for like for parity 0, so for maiden heifers, there was no evidence of a change after the value of 60. But for the other parities, actually what we saw is that the genetic differences between individuals steeply increased at higher THI levels. So roughly the genetic variance, but also the heritability at a THI of 70 doubled compared to the thermoneutral zone at THI below 60. And this was quite consistent across the 3 different lactations. We also looked at some genetic correlations. This is within the trait conception rate and within different parities. So the first correlation we looked at was between the intercept and the slope. So remember the horizontal lines and then the upward or downward going slope after it. And across the 3 parities, we found relatively small but positive correlations. And I'll try to explain in the next slide what that means. We also looked at the total breeding values or the realized breeding values for conception rate at THI values below the threshold of 60 and at values of 65 versus 70. And then we saw that at 65, those correlations, they're about 0.95, so they're quite high. If we look at a THI value of 70, they drop to as low as 0.8. And that at that stage, there's some potentially meaningful re-ranking at those higher THI values. So what does that look like if we just zoom in on a bunch of individual sires? So what we did here is we took the breeding values that we estimated for conception rate on the y-axis, and they are here plotted for the 20 sires with most daughters in the data. So those should be the sires that have the most reliable estimated breeding values. So here, all these horizontal lines are basically the breeding values for the intercept, and then thereafter we get this value plus the slope, the breeding value for slope multiplied by this deviation of THI from the threshold. So we do see that there are some important deviations after THI of 60. So just highlighting 2 sires in particular here, that below the THI threshold of 60, they have very similar breeding values, but then the daughters of the bull in blue here, they perform considerably better than average under hotter conditions, whereas the one indicated in orange, they actually perform poorer. And as a result, at a THI of 70, there's something like, in terms of the breeding value, 4 or 5% difference in conception rate. If you look closer, you also see a bunch of sires here that all sort of retain their ranking after the threshold compared to before, but there's also a couple that behave quite differently. So up until, if we just consider this value of THI 70, it's fair to say that there is some meaningful re-ranking here. So to try and tie this all up in a few conclusions, if we look back on our results at the population or the phenotypic level, the onset of heat stress for most of the traits where we could find a clear point of onset, it's about at a THI level of 60. So just to translate this back to what does that mean in terms of average daily temperature in the Netherlands? So that sort of corresponds to 16 degrees Celsius. Now that doesn't sound very warm. Do remember that this is an average daily temperature. So typically on these days, temperature may range between 10 and 22 at the warmest moments, which still isn't very warm. But then at that moment we start to see the first sign of heat stress. Comparing to results of others within the same project, it's actually this THI threshold in the Netherlands is lower than what is observed in countries with hotter climates. So basically, the further we're going south in Europe, we see that this threshold is higher. At the genetic level, we see that there's a considerable genetic variation in the response to heat stress. So in terms of genetic variation of these breeding values for slope, there's quite some differences. And also, we see that there's meaningful re-ranking of sires at higher THI levels, particularly if you get somewhere around values of 70. So based on this, if we foresee that there's going to be increasingly more days with THI values of 65 and 70 in the future, it's very worthwhile to consider heat stress and breeding values that are being used in practice. So for those that are interested, the results on the first parity, on the 4 first parity traits were published in Journal of Dairy Science last year, and the study for conception rate across the 4 different parities is at the moment under revision at the Journal of Dairy Science. And that's my presentation.
Thank you. Thank you, Mario. So I think we can start. Well, if you can stop the presentation, maybe Aurélie can start sharing hers. So Aurélie is a researcher in bovine genetics at INRAE. Her work in the RUMIGEN project focused on the effect of heat stress in dairy cattle farming and on the interactions between genetics and the meteorological environment. And her presentation today will focus on trade-offs between traits in the context of climate change. So, Aurélie, the floor is yours.
Okay, thank you, Eva. Do you hear me?
Yes.
No, it seems that you don't hear me.
No, yes, we hear you.
Oh, okay, perfect. So, hello, everybody. I'm going to present works on trade-offs between traits in the context of climate change in French dairy cows. Yeah, and this work was carried out as a part of the RUMIGEN project, and specifically in the task, the first 2 tasks of the WP3 of the RUMIGEN project. And the WP3 was based, as you say, you saw with Mario's presentations. It was based on the statistical analysis of the indirect measures of heat stress of heat tolerance by measuring the changes in performance under various temperatures or various THI. And this work was done in 3 countries, France, Netherlands, and Spain. And for the French part, I'm about to present you. It was carried out by INRAE and IDEL. So a bit about the data. We worked on the 2 breeds, the Holstein and the Montbéliard breeds. The performance of field data from the French National Database. And for production and health traits, the performance used are tasty milk production control. The traits studied were for production, the milk yield, the fat and protein yields and contents, and the health trait was the somatic cell score. This trait provides information about the infectious status of the udder and is genetically linked to the mastitis incidence. For the fertility, we studied the conception rate at first insemination during the first lactation, thanks to the dates and the results, calving or not calving, of the insemination. The meteorological data were provided by Météo France, which is a national agency, which estimates daily meteorological data for each square of this dense grid of 8 by 8 kilometers. And this data include temperatures and various temperatures and relative humidity, and we combine them in the THI, as Mario explained, which is the temperature humidity index. Oh yeah, for production and health traits, the THI we considered was the average THI over a 3-day period before the test day, whereas for the fertility trait, the THI considered was the average THI over 8 days after the insemination. And briefly on this graph, you can see the distribution of the THI values observed in our data, the THI values associated with the performances. And here is a result for the THI over the 3-day period preceding the test day. But the pattern, the distribution is similar for all the traits, with THI ranging from 17 to 80. And here I highlight 2 different THI. The first one is the THI 50, which is the average THI in all our data for all our traits. And this THI, the THI 70, which is a high THI for our dairy cattle population. And if I make the link with Mario's presentation, this THI is always above the threshold for all our traits. So it's high THI with sufficient data to make some statistics. So in my presentation, I will often refer to these 2 THI. So briefly, we start with the estimation of the evolution of the average performances along the THI gradient. And here is an example for the production of protein in Mobelia during the first lactation, and here are the results at the population level. I won't have time to explain more, and we have you had information in the Mario's presentations, and you can also watch the replay of the EcoGen webinar episode 2, during which Sophia Gers presents a large part of how French results, and more than French part. So, what interested us in this presentation is whether a genetic variability exists for this decline of production, in the level of production and in the decline in production. And we wanted to know if we can identify animals that lose more or less than others. And to do that, we use genetic models that account for interactions between genotype and environment. And yeah, the methodology is close to the one presented by Mario. So for this model, we used random regression models, but we don't use the broken stick model, but Legendre polynomials to models the genetic effect. And when we have repeated measures, we model the permanent effect with the same polynomials as the genetic effect. And for this model, we always consider the residual variances as heterogeneous. So with such models, the response of each genotype, and here you can find example of 3 animals. So the response of each genotype is modeled as a continuous curve along the THI gradient. And so we can estimate, we can have estimated breeding values that can vary along the THI gradient. So the ranking among animals may vary along the THI gradient. And if the breeding values varies, the genetic variances and genetic covariances when we deal with different traits, these variance and covariances may evolve too. So briefly about the number of animals with performance in our studies. For production and somatic cell score, we had 55,000 Montbéliard with performance and 72,000 Holstein cows with performances. And for fertility trait, we had to use more data because the genetic variability is a bit hard to estimate accurately. So we used 650,000 Montbéliard performance and more than 3 million of Holstein performances for the conception rate. Yeah, so first of all, thanks to this models, we estimated interactions between genotype and THI, and here you can see the within trait genetic correlation. Here at the left part for the conception rate, and here for the protein yield and the genetic correlation. The values of the genetic correlation are given by the color. For example, for the conception rate, the genetic correlation between the conception rate at THI 60 and the conception rate at THI 40, this genetic value is around 1 because the color is blue, so the genetic correlation is very high, around 1. And as you can see, for all these two traits, but all the traits, this genetic correlation are very high. So, and briefly, for the same trait at different THI levels, the genetic correlation are high with the minimum values for fertility around 0.75. And for production and health traits, the minimum values are above 0.8, and most of them are above 0.9, as you can see here, for example, for the protein yield. So in our data, we found little or no interactions between genotype and THI, and when observed, usually the high THI were implied. So we have few rankings in our data, fewer rankings of the animals. Fewer rankings, but we have genetic variances that evolve with the THI, so we have scale effect, and I will explain what is scale effect. So here you have genetic variance for production and functional trait for the Montbéliard breed, and the results are similar for the trend are similar for the Holstein. For example, for the production traits, here it's for the protein yield, but it's true for all the production traits. The genetic variance decrease at high THI. And the scale effect is that the consequence of the I'm not sure what is the consequence, but the fact is that the decrease in the genetic variance means that the difference between animals decrease at high THI for the production trait. And at the opposite, for the functional trait, health or fertility trait, the genetic variances increase at high THI. So the difference between animals become higher at high THI. The difference increases. Okay, and if we have a look on the estimated breeding values as a function of THI, here is an example with Montbéliard sires with at least 500 daughters with performances. And for two traits, the protein yield and the conception rate. So on the y-axis, you have the EBV for protein yield and the EBV for the conception rate. And on the x-axis, the range of the THI value. And on these graphs, I plotted only the 10 best sires for the protein yield at THI 50 and the poorest sires at THI 50 for the protein yield, and the same for the conception rate. The top 10 for the conception rate at THI 50, and the bottom 10 at THI 50 for the conception rate. Well, and thanks to this curve of evolution of the EBV, the estimated breeding value, we can define some kind of new traits. For example, the level of protein yields at THI 50 or the level of protein yield at THI 70, and same for conception rate at THI 50 or at THI 70, and the level is only the EBV at a given THI. And we also can define the slope, and the slope is approximately the same as Mario explained. And it's the same for the level. We can consider that the level is approximately the same as the intercept proposed by Mario in his presentation. So the slope gives the evolution of the ranking toward a decrease or an increase in the ranking of the EBV. And for us, it's a derivative of the EBV curve at a given THI. And in this presentation, we will focus on the slope at THI 70. Oh, yeah. Here you can see that some slopes are positive, but don't forget that these are EBV, so the EBV gives a ranking between animals at a given THI, not the forecasted performances. If you want, here I plotted the prediction of the performance, and you can see that at all sire families experience a decrease in production or in fertility as the THI increase. But some lose more than others. That's why we have different values of slopes. Okay, so if we come back to this graph, so you can see that here we can estimate some genetic correlations between these levels and these slopes. And here are the genetic correlation between all the production traits we studied, the somatic cell score, and the conception rate for the two breeds, Holstein in blue and Montbéliard in red. And as you can see, for the production trait, all the genetic variances are negative. And this is true for all the breeds, from moderate, minus 0.2, to relatively high trade-off, high genetic correlation between, for example, here the fat yield in the Montbéliard breed with a genetic correlation higher than minus 0.6. And this means that the animals with the higher EBV today, so the higher breeding values at THI 50, will be those that the most affected by its stress. The negative correlation means when you have a high EBV at THI 50, you have negative slopes, the most negative slopes at THI 70. So the best producers today will be the most affected by its stress situations. For health traits, the somatic cell score, don't forget that here the EBV is in the sense of the trait, the performances. So high EBV are for animals with high somatic cell score, so more cells and more risk of incidence of mastitis. So the positive correlation means that animals that are the most sensitive today will be the most, even more sensitive in its stress situation with more positive slopes and more somatic cell score, more and more cells. Okay, and for the fertility trait, the conception rate, for Holstein, the correlation is 0. So there is no consequence of the current selection on the slope under its stress scenario. But for the Montbéliard, it seems that the most fertile animal with the best EBV at THI 50, the most fertile under current climate conditions will be the least affected with the positive slopes at high THI. Okay, and let's turn to the bivariate analysis with trade-offs between production and fertility under different climate conditions. For production, we considered the mid-lactation protein yield, whereas for the fertility, no, it's all the same traits at before, the conception rate at first services. And only during the first lactation. We focus on the first lactation in our analysis. Okay, on this graph, you can see the genetic correlation between protein yield and conception rate along the THI gradient. And here we consider an equivalent THI for both traits because if you remember at the beginning of the presentation, I explained that the THI for production is the one before the test day and for the fertility, the one after the insemination. But here we consider the same values for those THI. For example, here is a genetic correlation between protein yield at THI 50 and conception rate at THI 50 for the Holstein, and in brown for the Montbéliard. Okay, so yeah, first of all, regardless of the THI, the genetic correlation between these two traits are low, close to 0 to moderate, up to minus 0.2. And this is probably because we focused on the mid-lactation protein yield, not the complete lactation, but only the mid-lactation data. And here is the genetic correlation between protein yield at THI 50 and conception rate at THI 50. So, and as the THI 50 is a current average situation, the genetic correlation is currently of minus 0.14 in Holstein and close to 0 for the Montbéliard breed. And if we go to warmer situation at its stress scenario THI 70, this correlation gets closer to 0 for the Holstein. And for the Montbéliard, the correlation dropped to minus 0.16. Okay. So they remain limited, but okay, they decrease. And yeah, if we come back to this two graphs, we can see that we can add some genetic correlations between traits. For example, the genetic correlation between the level of protein yield at THI 50 and the slope of decrease of the conception rate at THI 70. So you can see that for the both breeds, the results are, the genetic correlations are negative, moderate to quite high for the Montbéliard, minus 0.5. This means that high-yielding cows under the current climate conditions are expected to have a stronger decline in fertility under its stress, with more negative slopes. And if we look the opposite, the effect of the selection, the current selection on conception rate on the slope in its stress situation, the genetic correlation are positive, moderate but positive, and means that the current selection on fertility has a rather favorable effect on production, on the slope of decay of the production. Okay, and last, we can estimate the correlations between the two slopes, the slope of decay of the protein yield at its stress situation and the slope of decay of conception rate at its stress situation. And for both breeds, this genetic correlation is positive, very far from a correlation to 1, so it's clearly not the same traits, but they are positive. Okay, that means that cows with a smaller decline in production generally have the smaller decline in fertility. But the standard errors associated to this genetic correlation are very high. Acceptable for the Holstein, but clearly not for the Montbéliard, even if we have thousands, hundreds of thousands of data. So the standard errors is higher than 0.3 for the Montbéliard. And moreover, additional studies on another breed, Normans, shows different results with negative genetic correlations. So we have to pay attention if we want to deal with the genetic correlation with the slope. The breeding value, we have to pay attention with such genetic correlation between slope. So how to deal with this trade-offs in selection? It's a kind of take-home message, but they are a bit long. So maybe I can summarize. First, if we want to select on production traits, we saw that to go to more tolerant to heat stress animals, we saw that the high-yielding cows are those that experience the highest decline in production at high THI. Oh, yeah, so, but this result makes sense because it's not so, it seems so logical that the cows that lose a lot are those that produce a lot. So these are raw results, and so it makes sense. Another point is that it could be a good thing if this decline in production allows to preserve other functions. For example, the basal metabolisms or the health or fertility traits. And also we have to consider that adaptation to heat needs energy. And so if there is a reallocation of the energy to this adaptation to it, it can be a good thing. So that's why it's not a complete problem. So to have a decrease in production if there is a temporarity, if it's a temporary event. Well, for the selection, we can consider that a selection of the slope of decay is possible for production trait, the slope at THI 70, but it would result in a counter selection for production. And maybe it doesn't make much sense to select on this slope, so to select against the productions, because we select 4 productions for over a decade, so it's not so logical to select. For me, it's not so logical to select on the slope of decay. And if we want to have more tolerant animals with by decreasing the production, maybe we can use other methods, for example, the crossbreeding and so on. But we can use other traits to select for production. For example, we can select not on the average production, but on the production at heat stress situation, because it allows to anticipate future climate conditions. And it can be the same with functional traits, fertility and health. We can consider not the average EBV today, but estimated breeding values at high THI to anticipate. Another important point is that at the opposite of the production traits, the current selection on functional traits on levels at THI 50 is favorable for the future. And at least they are not unfavorable, but in most of cases, they are favorable. And in this case, the selection of slope of decay at THI 70 can be helpful because it will never be beneficial to select the most sensitive cows for and the most important slope of decay for fertility or for health. So the slope of decay can be very helpful for these traits. Okay, and last, about the trade-off between production and fertility, this trade-off will remain in the future, but they should remain limited. as we can see previously. But the work done here was done on THI level that remain fairly low. As you can see, we have few and no data recorded at THI 80. And we should have more and more data at THI 80 in the near future. So we will to be interested to update this study to see how the trade-off will evolve with harsher situations. So, and as we saw, the genetic correlation will evolve in the future, and probably maybe it's one of the not so bad news. Maybe this evolution of the genetic variances could make it easier to select for functional trait, because the genetic variances should increase in the future. Okay, so yeah, it's my last slide. I forget to mention the two papers. Sorry, you are here.
Okay, well, thank you, Aurélie. We will just reminding everybody that you can pop in your questions in the chat, and then we will answer them later. So we have now our next speaker, Martin, which is a researcher at the Agricultural Institute of Slovenia at the Department of Animal Science. His research areas are primarily focused on pig production, meat and fat quality, carcass composition, and characterization of pigs. His presentation will focus on the black-belted pig breed, summarizing recent research pig performance under various rating and nutritional conditions with comparison to lean modern pig breeds. Please, Martin, the floor is yours when you can share your presentation.
Thank you, Eva. Let me start with the sharing. Okay. Can you see everything in order? Yeah. Okay.
Yes, it's not full screen yet.
Take some time.
Okay.
Yeah. Okay. Greetings to everybody. So my presentation, as Eva already mentioned, it's about our research that we have been doing for the past 10 or 12 years with our local breed krškopolje pig. First, why are we so interested in krškopolje pig or local breeds in general? It's the aspect of sustainability that we tried to investigate here, and it's about the breed's potential for better adaptation, which enables the breed to be produced or to be reared in different environments, including those that are not so favorable for pigs, especially modern pig breeds. And of course, also to have higher quality and to research.
Sorry, Martin, we can't see the slides going. It's still on. Yeah.
Okay, I will try to stop sharing and do it again. Share. What about now?
Yeah.
Yes. Okay.
Yeah.
Perfect. Takes some time probably. Okay, our research is dealing with a lot of levels, including growth, including nutritional requirements, tissue growth, biochemical traits, meat quality, gene expression in association with metabolism. We also do some work on product quality, processing practices, selection possibilities, but this I won't be showing here today. So what I want to present you is different possibilities of rearing and comparison of these breeds, either in intensive, extensive system, and this was done lately in the past years during four big studies. And let me just tell you first about the breed. This is the only Slovenian autochthonous pig breed. It's characterized by a black coat and a white belt. The breed is the one that grows relatively slowly, at least relative to modern pig breeds, and it deposits a lot of fat in the carcass during fattening. In the past, this breed was reared mostly in extensive production systems, but now the pig breeders they use a lot of different practices, from pure intensive to rather or mostly extensive breeding techniques. The breed is aimed mainly for processing to high quality products. Mainly this is dry cured meat products like dry cured ham, fermented salami or stuff like this, and is characterized by good meat quality. Of course, as you will see from my results, this can be sometimes disputed or an area to be researched further. And it is reputed to be well adapted to local environment and dietary sources. The traits like performance, nutrition, feeding strategies, or metabolic properties still need a lot of clarification or studies. So this is the reason why we decided to invest a lot of our research in this. If I start with the first trial, this was a comparison of krškopolje pig with modern hybrid in pure extensive outdoor conditions. For this, we constructed a shelter and quite a big, I think it was 10 hectares of fenced area. And we settled the two groups there from late summer till the beginning of winter at similar weight, and then we recorded growth, feed intake, and production of these animals. What we noticed is that surprisingly, krškopolje pigs exhibited much better growth than modern breeds. This was probably, as we supposed, traits associated with better adaptation to harsh outdoor environment that they could cope with better. As expected, the breed exhibited higher fatness, but also higher quality of meat in terms of better intramuscular fat content. We studied the breed further. We done biochemical analysis and found out that this breed has more saturated, but especially more monounsaturated fat in the carcass, which is rather positive from the aspect of product quality. Lipogenesis potential was also associated to higher fatness, especially in the case of higher expression of gene for fatty acid desaturase and genes for lipidogenesis and adipogenesis. But surprisingly, we found that the activity of lipogenic enzymes in this breed was lower. This at first we could not explain, but later on we found that the breed is physiologically matured at much earlier age than modern breeds, so this could be associated with faster physiological maturity of the breed. Later on, we decided to at least partly repeat this comparison within indoor intensive rearing system, when again we use krškopolje against modern hybrid, starting at the same weight and applying three-phase feeding, and this time it was better controlled via automatic feeder and weighing system. In this case, opposite to previous findings in the outdoor, rearing, we observed that krškopolje pigs grows much slower at literally very constant average daily gain difference of about 130 grams per day. And also the difference in muscle deposition seems to be quite similarly constantly lower than in modern hybrid. Krškopolje pigs also increased in adiposity, and this was done at much faster pace than in modern breed. We took our investigation further. We compared carcass traits and meat and fat composition, and observed that krškopolje pigs exhibited much lower leanness, much lower muscularity, which is of course associated with lower deposition of muscle, but also had a quite good twofold higher intramuscular fat, which is very important from the sensory perspective of its meat. Again, we found out that krškopolje pig had more saturated fat, more monounsaturated fat, but less polyunsaturated fat. And what was also found interesting was that omega-6 to omega-3 polyunsaturated fat ratio was better in krškopolje pigs, so it means a little healthier, but still here we are talking about relatively high numbers, very much above the those that are good for our health. So this is numbers around 20, where what is okay should be around the ratio of 4, so still very high. The biochemical characterization showed that lipogenic enzyme activity, so lipogenic potential, was overall higher in krškopolje pigs, which explained the higher lipid deposition, but this was very tissue specific. As you can see, the situation in liver proved to be pretty much opposite. In terms of quality, krškopolje pig was proven to have a darker muscle color, which is beneficial from the consumer's perspective due to more myoglobin stored in the muscle, but also this negative trait in terms of higher muscle oxidation. This could not be associated to higher saturation, but probably just to higher intramuscular fat content. Interestingly, the modern pig breeds and krškopolje pig had quite comparable meat quality in terms of water holding capacity and meat tenderness. On the end, we also performed much deeper analysis with the adipose tissue transcriptome, trying to explain the differences or the metabolic processes behind the differences. And we observed that in krškopolje pigs, the genes that were upregulated were associated with either energy metabolism, then adipocyte proliferation and differentiation, extracellular matrix composition, presumably collagen growth, and some traits of inflammation, which was again rather strange to us, but after studying the literature data, we could see that inflammation is actually pretty much associated with adiposity or growth of adipose tissue. Finally, the gene set enrichment analysis pointed out that genes involved in immune response are responsible for the differences that we observed. Another study that was actually done a few years earlier we inside the breed try to compare two different rearing system, which is indoor conventional feeding using commercial feed against organic system that employed rearing in the fenced outdoor area with shelter and with organic feed, so mimicking the organic regulation. This means also supplementation of lucerne hay, alfalfa hay, along with the concentrate that was fed to the pigs. The difference was not so significant. There was some slightly lower average daily gain in organic pigs. They had also darker meat, but there were also some negative traits like worse water holding capacity and more unsaturated fats with lower oxidative stability. Here I'm not showing these results, but we also processed the meat from these pigs into dry cured ham and dry fermented sausages. And we found that organic material, raw material from these pigs may be rather negative. So although it's may be proven positive from the consumer's point of view or extrinsic quality, it may also cause some problems. So some caution is advised in this case. We also compared or tried to explain how the rearing system affects metabolic traits, including muscle fibers. And we observed that organic rearing caused a shift towards slightly more oxidative fibers and higher expression of type 1 or type 2A and type 2X related myosin heavy chain isoforms and low expression of this fast twitch 2B type. So we had a quite a strong effect on type, but when we tested the metabolic phenotype, this means genes that were related to muscle metabolism of fat and energy, we could not find whatsoever no difference. So at the end, we concluded that although there are effects, it's rather difficult to be associated with muscle fiber traits. The last study, which is done within the GEroNIMO project, it was really an extensive one. Here we compared two production systems that were used where we raised krškopolje pigs, where we tried to test the dietary protein reduction. So we had two groups. One was fed high protein diet. In the other group, these proteins were at some extent lowered. And of course, two rearing system, which is again organic outdoor system. There's a fence area with shelter. In this case, we applied at libidinal feeding of feed of organic origin. In conventional feeding, these were indoor pens, and the same amount of food was given than in organic system. In this case, the ingredients were the same, but were of conventional origin. The pigs were started this experiment at a similar rate and were fattened to higher weights of 160 or more kilos, which is a little high from the modern standards, but is quite common with feeding of this local krškopolje pig breed. At first, what we done with the results that we obtained, we applied modeling of nutritional needs using INRAE software, and we observed only some deficit in amino acid lysine, but this was again depending on the protein allowance and rearing system. Whereas in conventional system, high protein diet didn't cause any deficit. In low protein diet, this deficit existed but was relatively low, and it apparently didn't affect any protein deposition. In organic system, in high protein group, this deficit was present, but again, it was not so bad, still balanced. Whereas in low protein group, this deficit was much more evident, and it affected protein deposition. So this means lower protein deposition and higher deposition of fat compared to the high protein group. Furthermore, we went to test the effects on growth potential and carcass traits and meat quality. And in conventional rearing, we did not observe any large differences in growth on carcass traits between the two tested dietary treatments. In organic treatment, however, this low protein allowance actually caused slower growth, at least in the phases where the differences were the most evident. But interestingly, both systems and both dietary groups on the end exhibited similar final slaughter weight. And there was also small or no clear differences in meat carcass quality. So what we conclude from this examination that early protein restriction had only limited effects on the performance and quality in krškopolje pig. This is probably because the last phase where the nutritional needs were covered, there was some kind of compensatory growth that enabled them to equalize the final weights. This is pretty much a positive result. It shows the good aspect of this breed. We also continued the research trying to explain a little bit further, doing transcriptome and biochemical analysis. And the most interesting was the finding that we had in organic systems where pigs receiving low protein diet exhibited higher lipogenic enzyme activities. This is in accordance with the previous finding of higher lipid deposition, and also some effect on fatty acid composition, like higher monounsaturated and lower polyunsaturated fat content. As to transcriptome difference, we had higher expression of genes associated with lipid metabolism, higher oxidative stress, and higher mitochondrial function. So again, associated with increased metabolism, associated with energy. On the opposite, in conventional systems, there were almost no differences in biochemical traits, and some small differences in transcriptome, like overexpression of heat shock protein genes or innate immune system regulation of adipose tissue homeostasis, but whatsoever no difference in lipogenic regulation or lipogenic genes. So I come to these three general conclusions within this research. So it shows that krškopolje pig demonstrated distinct adaptability and fat deposition characteristic compared to modern breeds. So there is some potential to explore this further. And what we could very clearly see that subjecting krškopolje pig to different feeding or rearing practices, sometimes this is combined, offers additional possibilities to modify performance or at the same time quality and composition of either carcasses or their meat. And the findings observed for growth, fat deposition, and composition may be used to improve the potential for specialized or more sustainable production within rearing of this breed. So, come to the end of my presentation. I want to thank you for your attention, and also I want to acknowledge our financiers. The studies were financed partly by the Slovenian Research and Innovation Agency and also by the EU Horizon 2020 Innovation Program, which is two projects. One is GEroNIMO, the project that ended 3 days ago, and another is a treasure project that ended 7 years ago, but was pioneering the research of local pig breeds in Europe. Thank you very much.
Thank you, Martin, and thanks to all speakers today for their excellent presentations. So I think we can now open the question and answer discussion. So there has been some questions pop in the chat. I'll start. There are some questions for Mario first. So I can read here, do you investigate correlation between the animals that have a better resistance to THI in their fertility and other factors that can be affected by heat stress, like the yield, feed intake? I guess that also relates to Aurélie, but Mario, can you?
Yeah, so we did try to estimate, similarly to what Aurélie presented, the correlation between sensitivity to heat stress for fertility versus milk yield. And I would say that our results were not as conclusive as Aurélie's results were. So we did look into that, but we were not really able to draw very hard conclusions based on that.
Okay. So another question for you, Mario. Given the increase in temperature across Europe, how concerned are you about the future impact of heat stress on dairy production? And do you think current breeding programs are adapting quickly enough to address this challenge?
Well, I think one thing that's sort of reassuring is that specifically looking at fertility, that those that are that have a high fertility, some of them, they perform poorer under heat stress, but it's not like the ranking goes totally upside down. So there's still a fairly high correlation. So selection under thermoneutral conditions still should also yield genetic progress for fertility for hotter temperatures. At the phenotypic level, it's a bit harder to predict. So I mentioned in my presentation that if we go further south in Europe, the threshold, THI threshold for the onset of heat stress increases. So we're not sure why is that. Is that because the animals are more exposed to heat and therefore they're better adapted to it? Or is that because if there's more days with a high temperature, producers or farmers, they put more mitigation measures in place in their farms, and therefore they control the environment better? I mean, if it's the adaptation of the animals, then it could be that if it becomes hotter also in our country, that adaptation of the animals will at least sort of deal with part of that. But if the temperatures rise further, the problem will become bigger as well. That's for sure. Yes.
There's another question here. I'm trying to summarize. For Mario again, your analysis. Well, but if any of the other speakers want to intervene, but this is specifically related to your presentation. So the analysis always is related to first insemination within lactation, right? So some countries have to deal with animals that change farm in lactation due to alpine pasture, for example. A change on farm within lactation might come with a change in THI in parallel. So what's the effect on farm changes within lactation considering your project? Or do you have to deal with that actually?
Short answer is no. I think even if within the lactation animals changed herd, that we would have removed them from the analysis, because I mean, I understand the concern and the question, but from the modeling perspective, if the environment changes quite abruptly throughout the lactation, then it's a bit of a question. Is it the first or the second environment that affects the performance of the individual? So from a modeling perspective, we just try to keep the data clean for this kind of things. Yeah. So that's to try and model that kind of things. It's very difficult because you could also not find, well, at least not in our case, very many animals that would change herds.
Mm-hmm. Yeah. So, Aurélie, there is a question here for you. What would be the reason for the differences in the genetic cross-environment interactions observed in the French and the Dutch results?
Yeah, it's about the bivariate analysis. No, excuse me, because we won't have many difference between French and Dutch results. Even sorry, maybe between the intercept and the slope, because for the Netherlands results, this genetic correlation is positive, quite low but positive, if I remember well, for the Holstein, whereas for the French result, the genetic correlation is equal to 0 for the Holstein population. And clearly, I don't know why we had such results and difference. Yeah, I don't know, because our first results were obtained in Montbéliard, and for us, this was a good news that the correlation between the level and the slope is positive, or intercept and slope for the Marius presentation, because selection at whatever the THI we consider, and even if we don't consider any THI, the selection today is good for later performances. But when we move on to the Holstein, we observe no correlation. So I have no explanation, to be honest, why we have this difference. And I'm a bit confused because usually we have the same trends between breeds, and sometimes even within breeds and between breeds. And so it's not clear. It's not clear for me.
Okay. One more question. Is there any interaction between performance and fertility? That's it here. Yeah, not sure. I also.
Which kind of performance? Production performance?
Yeah, not sure what it means, the question. That's, well.
At least there are genetic correlations between production and fertility. I'm not sure that I understand the question. Sorry.
Sorry, not sure either. If we can, there is another question popping in at the moment.
Maybe I can just briefly respond to that. So what I showed is that for conception rate, we saw that there was heat stress for lactating animals, but not for maiden heifers, right? So that's an interaction between the production and the fertility, right? So if the animals are producing milk, they're heat stress, they're more easily heat stressed, which kind of makes sense because they need to eat more to produce milk, and that produces heat. So either it's already too warm and they still produce much more heat than maiden heifers, or maybe because of the heat, they start to eat less and also have less energy for not only milk but also for fertility. So yeah, so that's an interaction, I would say. Yeah.
Well, another question, the last question popping here. Can you please tell the relationship between THI and conception rate, and which THI is ideal for dairy cows?
Yeah, so based on our results, below 60 is ideal, right?
Yeah.
That's what we showed, and I'm not sure that maybe at very low values, maybe there's also then some repercussions, but yeah.
Martin, there's a question.
Same from the French cows. The ideal THI is the average THI we observed during the last 10 years, cumulatively.
Martin, there's a question for you. So based on your research, which production system would be optimal for the production of your black belted pigs?
Okay.
I can say the that's one. So
yeah, for krškopolje pigs, it depends on the aspect. If you are looking from animal welfare aspect, the answer is clear, I guess. It's outdoor extensive system. At least also what we see from the growth, it also improves variability between the pigs. This was one of the findings that I did not show. But from the point of view of product quality, there may be some problems with an unsaturation of fat, with lower growth. That may be negative. So if you ask me in overall, I would say outside extensive, but also with caution, because here we have to also take care of the nutritional need. With extensive system, the breeders are often not paying attention to covering nutritional needs. So this has to be overwatched closely. So the answer is not very straight.
if I might ask the last question, so you showed, Mario showed that there is considerable genetic variation in response to heat stress. So how feasible is to include heat tolerance into dairy cattle breeding programs?
Well, it's relatively easy to measure. I mean, both in our case and what Aurélie presented, the THI data is generated from information from weather stations, which is generated and it's available online. And then what you need is the traits, what you're looking at, that is sort of either longitudinal over different climatic conditions, or in our case, what we did is we modeled the phenotypes of daughters of bulls, such that for every bull, for every sire, you have observations of daughters under lower THI values, but also higher ones. So and this is all based on insemination data that's just recorded routinely and used for breeding value estimation. So in principle, the information is all there. It just needs a bit more work to get this perhaps into robust models implemented in breeding value estimation. But there's no big roadblocks to that, I think.
Well, thank you to all of you. I think there is maybe one or two questions that have been not answered yet, so we might be able to answer them online. So just to thank all of you, and to I'm gonna share my last slide for you all to encourage you to subscribe to the RUMIGEN newsletter. So again, thank you to the speakers and to all of you for joining, and have a good day.